don't, if you do go, don't get the s'mores beer. I didn't even order, like, I waited in line to get it, and then I saw it, like, on display, and it looked just disgusting. So,
S'mores beer?
yeah, so I just got it out of line.
Okay.
It was like a really dark, like a Guinness colored beer
Yeah.
with like a graham cracker cruster on the rim and like a half-assed marshmallow floating on top.
Ew.
That
Yeah.
doesn't sound good.
It did not sound good. Like, it sounded good, but then when I saw the display, it was like, ugh.
Okay, so last time we had stopped, we were starting to talk about free particle solutions to the Dirac equation. And so we had written down the Dirac equation. Right, and we had shown that it also said that the spinors also satisfy the Klein-Gordon equation. But we had said that, that the Dirac equation is a little more fundamental because with the gamma mu in there, it's containing some information about spins. Right? And so we said, okay, well, if it obeys the Klein-Gordon equation, then it must be something like a plane wave, right? Because it's just a wave equation. And so we wrote down a plane wave solution, which we call, this is what we call a positive frequency solution. So we're only considering one possible sign, basically, of that exponential. And this thing's a column matrix, right? So we have to put in some column vector. Right? And that column vector in general can depend on the momentum. So we took this guy and plugged it in here. Right? What's it going to do? This is the forward derivative is going to hit this exponential, pull down a factor of minus IP. Right? And so you get a constraining equation on the form of this guy, minus m. All right, so this is the guy that we're after. If we want to solve this, we've already separated off the wave dependence. Now we just need to find this column vector. And our approach was to solve it in the simplest possible frame, which is the rest frame. So our approach was solve this in the rest frame, where this guy is just the mass, and the three component of the momentum is 0. Right, and then we'll boost. So we'll solve it for this, and then we'll perform a boost to some general frame. That's what we're going to do today. So we said, all right, well, let's specialize to this case. So the only non-zero component is P0. So that means from this equation, I'm just going to have gamma 0 P0 minus m hitting our U of P. And if I plug in what gamma 0 is, remember it's the off diagonal, so it's 0. And then remember that, hidden here is an identity matrix. So this is going to be a minus m, 0, m. And this is all hidden U of P. Cut off the board, but it's okay. But we can put this stuff together, and we get a nice little matrix equation. Minus m, minus m, and hitting U of P. Right? But U of P, we want to find the solutions for it. So remember, we're writing, it's a 4-component spinner. We want to write it as two components. So let's write it like this. And if you multiply this stuff out, it's apparent that A has to be equal to B. And so we're free to choose, we're free to choose one of these, and then this equation constrains the other one. So we chose this guy to be called C, is the convention, right? And then we threw in, so our solution looks like this. So A and B are both C. Right? And then we threw in a normalization constant, which goes like the square root of m. Okay? And we'll see why we had to do that today. All right, so we see that after applying when you apply the Dirac equation, you basically only, this constrains you to basically you can only choose two of the four components of your spinner, right? And that's what we would expect for a spin 1/2 particle, right? So right now, irregardless of what we were saying the other day, we said that that this thing transforms under the normal SU2 type of rotations, right? But there's nothing here so far that says that we have a spin 1/2 particle. Okay, we're assuming that we've constructed the equation for a spin 1/2 case, but we haven't really shown that yet. Okay, and but the fact that we can only choose two, we're only free to choose 2 out of the 4 makes sense because in the case of say the spin along the z-axis, right? You would expect that these guys would be, you have one choice which would correspond to the spin up, and you have another choice which would correspond to spin down. Okay? So it looks like we're on the right track, but we're going to have to wait a couple lectures from now to really see that what we're describing here are particles with spin 1/2. Okay, so we've got the solution in the rest frame. Okay, now we need to boost this to some general frame. Okay, so the easy part's done. Right, now we have to boost it to some general frame. And before we go off and just try to apply a boost to this, let's remind ourselves what the boost looks like for a 4 vector. Okay. So remember, this thing transforms under different representation than a 4 vector, but we can learn how to perform this boost by looking at this case, the 4 vector. Okay. So in particular, let's look at the 4 momentum. Right. And let's say we're in the rest frame and we want to boost it along the z direction. Okay. So I'm in my rest frame. There's going to be something here. So I'm in the rest frame. So my 0 component is m, and everything else is 0. Okay? I want to perform a boost along the z direction. Okay? So what I'm going to have after I perform the boost is some energy and then some component of momentum along the z-axis, right, which I'll denote by P3. And you have to go back and look at how we define infinitesimal boosts or rotations, or infinitesimal Lorentz transformations. But if you do, you go back and you see that we wrote these things like this, where we have some small parameter, so we're always continuously connected to the identity operator, right? And we have some small parameter, and I'm going to call that eta, right? And then a boost along the z direction, the matrix, the generator matrix looks like this, right? So this is, like I said, this is a small parameter, so there's no way I'll be able to spell infinitesimal, so I'll just say small parameter. Very small, okay? So this is what we would have for an infinitesimal boost along the z direction. But we want a finite one, right? So what do? Well, we just compound a bunch of these small ones, okay? And when we compound these guys, we get an exponential. Right? But it's an exponential that has eta and then a matrix inside of it. 0, 1, and 0. And so that way, hitting m. Okay, and you look at this thing and you think, oh my God, how am I going to apply this, right? Okay. Well, what you want to do is basically expand out the exponential. Okay, so let me over here kind of sketch it out for you. Okay, so you want to take your exponential, which is eta, and then this matrix 0, 1, 1, 0, right? And you want to Taylor expand. Okay? So it's 1, and identity matrix. Let me just write it out explicitly. 1, 0, 0, 1. How far can we push? Can't go that far. Okay. And then the next term would be the first order term, right? And the first order term is going to have this matrix. And then I would have the second order term, which is going to have two factors of this matrix. And then I would have the cubed term, which is, so this is 2 factorial, this is 3 factorial. So you see what I'm doing? I'm just doing a Taylor expansion, right? Which I have 3 factors in this matrix here. And so on and so forth. Okay? But then you look at this thing and you say, okay, let me multiply these matrices out. Right? And when I multiply these two matrices, I get the identity matrix. Right? So you can see this first, the 1, 1 term is going to give me 0, 1, right? You multiply them out, so this gives you the identity matrix. 1, 0, 0, 1, right? So that means that this thing's identity matrix. And when it hits this, it just gives me back this matrix. Right? All right, everybody with me so far? Okay. So then I multiply through the etas, right? And what I see is that this thing basically, when I can resum it, right? And it's a sum of two terms. It's a sum of a cosh, right, times identity matrix plus a cinch times our generator matrix. All right, and how do I see that? Because I see that I know cosine or cosh always starts at 1, right, for small angles, right? So it's going to be this piece, right, and then it goes like even powers of eta. Right, so it'll be like this, this, and then the fourth term, the sine piece, the sense piece is going to be coming from this guy, right? Starts at order eta, right? And it would give me the eta cubed piece, and so on and so forth. Okay, so if I Taylor expand this guy out, and I group the matrices together, I see that the coefficients can be resummed. And when they resum, I get cosh and cinch. All right. So what I have here is this exponential, but let me rewrite it in terms of the cosh and cinch. So I have that thing over there, and when I plug it in here and I multiply through, I end up with m cosh eta m sin eta. Right. So what I've done is I'm trying to save writing. I'm trying to take this, I'm taking this, plug it in here, right? And then I multiply through onto this spinner, and the only things that survive are these two terms. Okay. And this eta, you learn about it in Jackson, chapter 11 or 12, whatever special relativity is. It's called the rapidity. Right? And rapidity is a nice quantity because it's the thing that's additive under boosts. Okay. All right, so that's how you want to do these boosts. Okay, so this is the case with a 4-vector. Right, so this is nice and simple because the generator matrices are just these block diagonal either zeros or identity matrices. All right, but now we want to try to perform the boost on our spinner. Okay. All right, so in the case of our spin 1/2 representation, we know that our Lorentz transformation matrices look like this. So it's an exponential, it's minus I over 2, and then it's omega mu nu S mu. All right, so that's what we have. And we're going to consider a boost along the z direction. So in that case, this thing is going to be S03, right, which is minus I over 2, sigma 3, 0, 0, minus sigma 3. Okay, so that means that this thing here, the only pieces that are going to come out of this are the omega 03, right? But there's going to be two terms there, right? When we sum over the mu's and nu's, there's going to be one term that goes like omega 03 and S03. There's also going to be a term that goes like omega 30 S30. Right, so it's going to give us a factor of 2. So just keep that factor of 2 in mind, because when I put all that together, and let me call this, so what I'm going to do is call this omega 3 just to be, I've got arrows going everywhere. This omega 03, we're going to call it root. It's going to be root. Okay. All right. So if you follow the arrows, you find that this matrix can be written as minus eta over 2 and sigma 3, 0, 0 minus sigma 3. Okay, so that's what our Lorentz transformation looks like, or for the specific case of a boost along the z direction. Okay, so now we want to go and apply it like we did for the case of the 4-vector, but now we're going to be applying it to a rest frame solution to the Dirac equation.
Is it eta over 2 or over 4?
It's 8 over 2, right? Because it looks like it's 8 over 4, but that's what I was trying to say right here, is that there's a factor of 2 that comes in that cancels off, because these two terms are equal. Right, so when you sum these up, you get a factor of 2, and it kills off one of these factors of 2. Right?
Because there's already a factor 1/2.
Right, so when I plug this into here, I get minus 1 over 4.
Okay.
Right? And then I get a factor of 2 here, and it cancels off.
I forgot the S had a 1/2.
Yeah. Okay. All right. So what do we have? So we have, we're looking for a spinner in a general frame. Well, we're doing it along the z-axis, but we're going to see that that's general enough. Okay. So I have my exponential minus 8 over 2, sigma 3, 0, 0, minus sigma 3. Hitting our solution, which is square root of m, c, c. Okay? All right. So we do the same thing. You do that stuff that I was talking about before, where you expand this out, right? And then you resum it. You resum the coefficients, right? And what you find is that in this case, it's a little more complicated. It's a cosh of 8 over 2 times identity matrix. then minus sinh 8 over 2 times this matrix. And still multiplying our square root of m. All right, so I'll let you work it out at home. All right, that going from here to here, I basically follow the same steps as for the case of the 4 vector. All right, so now for the real doozy. Okay, so you can put all this stuff together, right? And it turns out to be beneficial to rewrite these guys in terms of exponentials using handy dandy Euler identities. Right? And you get this giant matrix. Okay, so I have eta, e to the eta over 2, and then 1 minus sigma 3, 2, plus e to the minus 8 over 2, 1 plus sigma 3, 2. Okay, that's one of the terms. That's the 1, 1 component. And then I have e to the 8 over 2, 1 plus sigma 3, 2, plus e to the minus 8 over 2, 1 minus sigma 3, 2. That's that. And there's a big fat 0 here, a big fat 0 here. And this thing is multiplying our m, square root of m, c. Okay, so that's where so you're going from here to here. I've just rewritten this Cauchys and Sinches in terms of exponentials, and then combine the two. Right, and when you multiply that out, you get that this spinner looks like this. So it's a square root e plus p3. So I'm replacing now any factors of square root of I figure out what I'm doing. Is let me write it out. Try to figure out what I did. So this is 1 minus 3. This is plus square root e minus p3. 1 plus c. The other part is plus square root plus p3. 1 plus sigma 3, 2, square root e minus p3, 1 minus. Okay, so what did I do?
Okay, when you boosted that M0, at first, that you said we want to boost
Yes.
this,
The 4 vector, yeah.
yeah, we got a relation between E and P3 and M and eta. I guess you've substituted.
Okay, yeah. Yeah, thank you. Yeah, I would have never thought of that. Yeah, so that's what I'm doing. So I'm using. Right. So we had. Yeah, thanks for saying. So we had found that P3 is equal to M Cosh, and P3 is equal to M Sin. Right, so you can write these guys in terms of the exponentials and then get those relationships. Okay. And all this stuff, unbelievably, can be simplified to this. So U of P is equal to square root of P dot sigma C and square root of P dot sigma bar. Okay, so these are the 4 vector sigmas, right? So remember, this is sigma. Sigma mu is 1 sigma. And sigma bar mu is 1 minus sigma. Right. Okay? So I'm going to leave it, again, a homework exercise to go from there to there. Unbelievably, that mess can be written like that. Right? And not only is this thing compact, right, but it also applies to any general boost. It's good for any boost. So we started out, just trying to boost along the z direction, but we ended up getting an equation that is good for any boost. Okay, and you might think these square roots are weird. The square roots, just know that when you take the square root for a particular case, you always take the positive root, okay, for each eigenvalue. And then dealing with these guys, there's a useful identity. It's related to one that I remember from quantum, but it says that P dot sigma and times P dot sigma bar is just equal to P squared, and P squared is just equal to M squared. All right, so we've got a solution, right? And like I said, we're always free to choose 2 of the components, right? So we can work with our familiar spinners, right? So in particular, we can choose, say, we could choose plus C plus, which is 1, 0, so I can spin up on the z-axis, and we can choose C down as 0, 1. Okay. Well, let's see how this thing applies. How this thing applies under boosts, under large boosts. Okay, so for these particular solutions. All right, so let me take the U solution where I'm plugging in here for C. I'm plugging in the plus. So let me call this C plus or U plus. Okay. And if I go back to the expression before that one. Let's see. Oh, okay. So I'm taking the C, right, and I plug it into the big long equation, and I operate it with the Pauli matrices, right, and I end up finding that this guy can be written as square root P minus P3 times R1, 0, right, and then square root E plus P3. Okay. Likewise, for the spin down case, I get plus P3 up here, 0, 1, square root E minus. Okay. So now we want to ask ourselves, what happens under a large boost? Under a large boost, all the energy is going to be coming from the momentum, right? Okay. So in that case, under these large boosts, E, it's like the ultra-relativistic limit. So E is going to be given by P3, right? Somebody say yes.
Yes.
Okay, thank you. All right. So what happens in this case? Well, under these large boosts, this guy is going to go to 0, right? And so U is going to end up in something like the square root 2e, right? Because P3 is approximately e, an ultra-relativistic limit, and we get a big fat 0 up here, and here we get the 1, 0. And under this guy becomes 2e, but in this case, it's spent down. All right, so what are we seeing? Well, what we're seeing is that in the large boost limit, right, our solution, our four component, spinner solution is decomposing into two component spinners. Okay, which is exactly what we would want, for our spin 1/2 case, right? For massless particles, spin 1/2, okay, with the spin 1/2. Right, and if you trace it back, you'll see why we had to put that square root of m into our solution. Right? Because what happens is it keeps the spinner expressions finite in the massless limit. So when we take mass going to 0, this thing gives me a 0 multiplying something that would be blowing up. Okay, so that's why we needed that factor in front of our solution. Okay. All right, so let's want to work through the normalization of these guys. So we want to be able to write down. Good.
For this, after the large boost, the solution is telling us that it can't change from spin up to spin down. Like it won't change. It has to maintain the same spin.
No, I don't think that's what it's. I think it's telling us that what's happening is 4 component solutions are decomposing down into just a 2 component solution, right? Because the other 2 components are just 0. Right? So it's your 2 cases that we're calling spin up and spin down, which originally are 4 component, are reducing to just a 2 component, basically to 2 component spinners.
I mean, just the way I see it is, if we're choosing to be spin up or spin down, doesn't that like automatically reduce it to being a 2 component?
No, because this is a 4 component spinner, right? It has 1, 0, 1, 0. Right? We have to. Our solutions have to be 4 component vectors.
And so by making the boost,
you're getting closer to the quantum mechanics.
Uh,
by making the large boost, we kind of eliminate 2 components,
right.
and it just reduces down to something to 2 component instead of 4.
Yeah. Make sense?
Yeah.
Okay. All right. Yeah. So we want. Okay. So what I want to do next is work out the normalization. Right. So we want to be able to write down, just like we talked about when we talked about the 4 component spinner itself. Right. And we said we want to be able to write down Lorentz invariant terms. Right. Say for Lorentz invariant scalars for the Lagrangian. And we showed that this guy, when we took psi dagger psi, which would give us a scalar, is not Lorentz invariant, right? So this is not Li. Okay? And so the way we worked around that was we introduced a gamma 0 in here, right? And we defined something called psi bar, which was psi dagger gamma 0. And then we said, okay, well, it's psi bar psi Lorentz invariant, and we found that yes, it is. That was last time. So I want to do something similar for our spinners, our U spinners, okay, our positive frequency solutions. So let's try that. Okay, so let's take U dagger U and work it out explicitly, right, using our solutions that I just erased. All right, so U dagger is going to be C dagger. All right, this thing that's multiplying is just a scalar, so Hermitian quantity. And then my U is square root P dot sigma C square root P dot sigma bar. Okay, so I want to carry out this matrix multiplication. And what it gives me is, so both terms are going to give me C dagger C. Right? And then from this guy times that, I'll just get P dot sigma. From this guy times that, I just get P dot sigma bar. Okay, but remember these are the four vector dot products. This gives me C dagger C. Right? And this is going to give me, what does it give me? E dotted into 1. Right? So it's giving me E, so it's about E sub P. Minus P, minus P dotted into sigma vector. And this guy gives me plus E, P, or it gives me remember there's a minus sign in this guy, the three components, so the minus sign goes off the minus sign from the metric, it gives me a plus P dot sigma bar. Okay, and so these two guys cancel out, and what I get is that is U dagger U is equal to 2 times P C dagger C. Okay? And this thing, because it depends on the momentum, is not Lorentz invariant. Right? Okay, so we have to, just like in the case of the four component, the psi, we have to try to fix this. Okay? And the way we fix it is the same way we fix the case of the size. We put in a gamma 0. Right? So I define U bar of P, U dagger of P times gamma 0. Okay? So that means that when I take U bar U, I have C dagger, sigma, P dot sigma bar. And I have this gamma 0 now in the middle. 0. Okay? And what it's going to do is effectively flip-flop these guys, right? Flip-flop the components of this column vector. And so that means that when I multiply all this out, I still get the C dagger C. Okay? But now I'm going to get square root of P dot sigma times P dot sigma bar plus square root P dot sigma bar. Right? And this thing inside the square root, I said was an identity that you run into a lot, right? It's m squared. Right? So it turns out to be m squared. This is m squared. Right? When you take the square root of m squared, you get m. So even I can do that one. Right? And so I end up finding that my normalization condition here is U bar U is 2 times m C dagger C. This thing is, because it's mass is just a scalar, it doesn't depend on the momentum, but this thing is Lorentz invariant. Okay. All right, so then you ask yourself, okay, well, what if we're talking about massless particles? Right? In the case of massless particles, you have to go with this guy. Okay, but there's a workaround. There's a way to fix it. Okay, and we'll talk about that later. Okay, but for the time being, if you want a Lorentz invariant quantity for massive particle, you want to go with 3 bar d. Okay, but in the massless case, this is going to give you 0. And that's not a good normalization condition. All right.
That means your
Okay.
particle has no probability.
Huh?
Particle has no probability of
Yeah, yeah.
anywhere.
Yeah, right. Okay. All right. So let me just summarize what we've done so far. Okay. So we've basically only worked out half of the solution. We've worked out what we call the positive frequency solution. Positive frequency part, right? And that was that psi of x equals u p e to the minus I p dot x, right? And we're saying that p squared is equal to m squared. So we're working in the right metric, and the minus sign, along with this condition that the 0 component of p tells us that we're dealing with the positive frequency solution. Okay, and we found that there's 2 linearly independent solutions within this positive frequency solution, and those are given by US. Okay, and this S is what we call spinor index. Right? And these solutions look like this: square root of p dot sigma, square root of p dot sigma bar. Right? And there's 2 of these solutions, right? So CS. Okay? And here S is just an index, like I said, it's 1 or 2. For example, and my example is typically we work in the Z, that's Z basis, right? And so this is C1 will be spin up, and say C2 will be spin down. And then we just showed that the normalization conditions for these U's, is this for a massive case, or if you have a massless particle, then you have to work with this guy, 2EP, C dagger C. And along with the fact that C dagger C, we typically we normalize these guys to the 1. So if I want to include the spinor index, I would have URS. And this gives me 2 times the mass, and this thing would be, let me just write it out. So it would be C dagger R CS, and the normalization condition for these guys is that it's a delta function, Kronecker delta function, so it's delta RS. Okay, and the same thing here, that if I put in the spinor indices, it's RS, this will give me delta RS. Okay. So that's what we've done so far. All right. And like I said, it's only half of the solution, right? We still have to work out the negative energy solution or negative frequency solution. But in that case, you can go through all this stuff and you find basically the same thing with a few small changes here and there. Okay. So I'm just gonna use this and just change the notation. So for the negative frequency solution, our solutions look like there's a plus sign here. And because we're choosing this plus sign, that means that we're still working with, even though, we're calling them negative, so this would be negative frequency, right? But we still have positive energy. Okay, so P naught, the 0 component, is still greater than 0. Okay? And these have to be, in general, these have to be a different column vector, so we call them V. Right? They still have to depend on the momentum. Okay? And then here, these two component spanners are in general different. So here we'll call these eta. And along the way somewhere I pick up a minus sign here on this guy. So this is V. Okay. And this still goes. So S is can still be 1 or 2, and eta can still be spun up or spun down. And these guys obey basically the same normalization condition. The only difference is you pick up a minus sign. However, in this case, you still get a plus sign. And then finally, you ask how are the U's and V's, how do they act, do they play well together? And it turns out that they're orthogonal. So it turns out that if I take U bar R, say, in VS, or V bar R in US, the same as you can do. Okay. So that flushes out our whole spectrum. Okay, we've completely solved the Dirac equation. We've got the positive frequency solutions. We've got the negative frequency solutions. So now we're almost ready to quantize the theory. Okay, still here, haven't quantized the theory yet, but we'll do that next time. Okay, so I'm going to stop here, and we'll pick it up at that point next week. Okay. So it's a lot of stuff to work through. I'll put my notes in the Dropbox, and like I said, some of those steps you just have to work through them, at least once in your life to convince yourself, of certain things. All right, and make sure double check me on my algebra and all that stuff. All right, because I could be off. But anyways, so just let me know if you have questions. And I'll try to think about a new homework set, and I'll get the first one graded this weekend. Okay. All right. Okay.